If f of x is arcsine of x, what's f of negative square root of 2 over 2? The answer, of course, is negative pi fourths. Yeah, very good. It's not 7 pi fourths, which is coterminal with negative pi fourths. It's negative pi fourths. You go straight down clockwise into quadrant 4. Good. Okay. All right. So let's start doing compositions now. Again, the capital letter, if you see it without function notation, the capital letter is there to denote that we are talking about the inverse sine function, one answer in the PVR, instead of the operation where you find all of them within a certain interval. All right, so you got cosine of inverse sine of 3/5. This is composition. So normally we start from the inside out. So we'll take the inverse sine of 3/5. That'll give us an angle, right? This is going to give us some angle theta. And then we turn around and take the cosine of theta, and we end up with the ratio. Would you agree? So we're starting with a ratio of 3/5, and we're ending with the ratio, the cosine ratio of the angle whose sine is 3/5. That's how we read this. Now, if we try to evaluate it from the inside, inverse sine of 3/5, we know what quadrant theta is going to live in, don't we? Which quadrant in the PVR is sine positive in? Quadrant 1. So not quadrant 2, that's not in the PVR. It's going to be some quadrant 1 angle theta. Is that on the unit circle? 3/5? Is that one of the ratios from the unit circle? It is not. It is not. So when it says to find the exact value, that means no calculator. How are we supposed to do a problem like this if we do not know the angle from the unit circle whose sine is 3/5? Well, I'll show you. We really don't need the angle because we're starting with a ratio of 3/5 and we're ending with a ratio as well, aren't we? I just said that. We're ending with the cosine of that angle's ratio. So let's just go ahead and do this. This is like a two's clues problem, if you will. I know sine ratio is 3/5. So this is 3 and this is 5 in quadrant 1. Would you agree? That's the sine ratio. Okay, they gave that to us. If I know 2 of the 3 sides of the right triangle, don't I know the third? Yeah, so by the Pythagorean theorem or by your Pythagorean triple, what's the other side? Should be 4, right? So that's a common Pythagorean triple. Your 3, 4, 5 right triangle. Otherwise, you do the square root of 25 minus 9, which is the square root of 16. The square root of 16 is 4. Okay? So if you wanted to do the Pythagorean theorem, you would say x is equal to the square root of 25 minus 9. And you can get the x value. Now that we know all 3 sides of that angle, we don't really need the angle, don't we? Because what's our final answer? It's the cosine of that ratio. And what's the cosine of that triangle? X over r, which is what? 4/5. There's your answer. So it's like a two's clues problem, but the clues themselves are embedded inside the problem. We're only looking for one ratio, and one of the clues itself is the PVR. Like we know that the angle is not going to live in quadrant 2, even though sine is positive there, because it's outside the PVR. Got it? See what I did there? Okay, your chance to do this one on your own. Go. Did you get 3/4? It's the same triangle, isn't it? It's the tangent this time of the angle whose sine is 3/5. That's how you read that. So again, if you want to draw the triangle in quadrant 1, you got y is 3, r is 5. So the x is 4, or use the same diagram. Now we don't really care what the angle is. Arcsine of 3/5 is going to give us an angle theta, but we want the tangent ratio, and tangent's y over x, which is 3/4. So we can use the same diagram for part C. What's the cosecant ratio of that same angle? 5/3. Ooh, did we even need to draw the picture for that one? No, because I gave you the sine ratio, and I'm asking for the cosecant ratio. And how are they related? Reciprocals. Yeah, good. You found the right word. You almost said inverses. They're reciprocals of each other. Sweet. All right. Okay, so let's go ahead and look at this. What if we're taking the composition of a function and its inverse function back to back? Usually they just undo each other, right? If I do f of x and then I do f inverse of that, I should get right back at x. And the order doesn't matter. I could do f of f inverse of x, and they should send me right back where I started, right? So start with x, 2 steps to the right, then 2 steps to the left. You're back where you started at x. Or start with x, 2 steps to the left, then 2 steps to the right. You're still back where you started, right? Now, you got to be careful when you're composing sine and inverse sine back to back, because it's not always going to be x. It is not always going to be x. So let's think about it. Let's look at the top one. If I start with arc sine of x on the inside and sine on the outside, this means I'm starting with a ratio. Okay? And if I take the inverse sine of that ratio, I'm going to get an angle theta in the PVR. It's going to automatically be in the PVR. What happens then if I take the sine of that angle? Well, I will get right back to where I started with x, as long as the x is between -1 to 1 to start with. In other words, as long as it's a legal ratio, when you have an arc sine on the inside, it's always going to be x. So this one will always undo each other. Will always undo each other for legal ratios. The top one will. But the bottom one, not so much. You got to be careful. The bottom one, we're starting with an angle. And that angle can be anywhere on the unit circle. It doesn't have to be in the PVR. It could be anywhere. So if you're taking the inverse sine of a sine of an angle, it's not always going to just give you x, because that x might not be in the PVR. This one, this x, must be in the PVR, because we're taking the arc sine of it. And anytime we take the arc sine of something, it has to land in the PVR. So when does it undo itself? It undoes itself if the angle is in the PVR. If the angle is not in the PVR, we actually have to find the angle in the PVR that has the exact same sine value as the original angle. Now that might be kind of confusing for you, so let's just try it out with some examples, and we'll drive that point home, okay? All right. Let's look at example 6. Evaluate the following compositions without a calculator. Okay. Inverse sine of -0.0316. We're doing that on the inside, and then we're taking the sine of the resulting angle. So it's sine of inverse sine. That's the first thing you want to notice. It's sine of inverse sine. These are inverses of each other. And we're composing them back to back. So could the answer be -0.0316? Yeah, it could be. But we just got to think about the sequence here. This is an angle or a ratio? What is it? It's a ratio because it follows an inverse trig. So when I take the inverse sine of that ratio, I'm going to get an angle theta that is in the PVR. In fact, what quadrant will it be in? It'll be in quadrant 4. We know that for a fact. It'll be in quadrant 4. Okay. What happens then if I take the sine of that same angle in quadrant 4? Should I get the same ratio? I should, right? I should get the same ratio. In other words, if you draw it out like this, here's quadrant 4. I know that this is -0.0316, and I know that this is 1, and I don't really even know what the x is yet, but there's my theta. I set it up like that. Now, what's the sine of that angle? Well, the sine is y over r. I get the exact same answer, don't I? -0.0316. So, yeah, if you're starting with the ratio, and as long as it's a legal ratio, it's between -1 and 1, it's going to undo itself, and you're going to get the same answer that you started with. Okay? Because you're just setting up the triangle, and then right away you're taking that same ratio back off the same triangle. So starting with the ratio is okay, as long as it's a legal ratio. Look at B, though. B, we're starting with the inside with an angle. And you do notice, by the way, that you're doing the inverse sine of sine. So once again, these are inverses of each other. Now, is pi fourths in the PVR? It is. So should these undo each other? They should undo each other because I go to pi fourths, which is right here, and I know it's in the PVR, and then I take the inverse sine of pi fourths. This would be the square root of 2 over 2 over 1. And then I take the inverse sine of that ratio, and I get the same angle pi fourths. Pi fourths is in the PVR. So it's my final answer. They undo each other. So far, so good? All right. Letter C. Again, you notice we got arc sine of sine. So once again, we got inverses of each other composed back to back. Is the answer just 3 pi fourths? No. We're starting with an angle now, but it's not in the PVR. And since the last thing that we're doing is taking the arc sine of that ratio, that angle has to be in the PVR. This angle that we end up with must be in the PVR. So here's how you do a problem like this. When in doubt, just work it out from the inside out. When in doubt, just work it out from the inside out. 3 pi fourths is over here, isn't it? It's in quadrant 2. What's the sine of the square root of 3 pi fourths? Well, it's the square root of 2 halves over 1. So it's positive. It's positive square root of 2 halves. What's the other quadrant where sine is positive? Quadrant 1. Okay? So that's the other quadrant where it's square root of 2 halves over 1. They have the exact same sine ratio then, don't they? What's the angle in the PVR that has the same sine as the angle in quadrant 2? Pi fourths. So that's how we do it. Remember, there's always two angles within one rotation that share the same trig sign, same trig value, right? For sine, it's quadrants 1 and 2 where they're both positive, and 3 and 4 where they're both negative. For cosine, it's 1 and 4 where they're both positive, and 2 and 3 where they're both negative. And then for tangent, remember, they're in opposite quadrants. 1 and 3 or 2 and 4. There's always two quadrants. So if we're in the wrong quadrant, we just got to get into the right quadrant. Okay? All right. Got it. Y'all try this one. Maybe. Depends where 13 pi tenths lands. These are the more fun type problems. So that's why we're building up to this type of problem. This might be the one I give you on a quiz or a test. Talk about it with your math buddy. Do a little think, pair, share, or a little shoulder talk. Hey, what's up, shoulder partner? What are your thoughts on this problem? Yes, y'all do. Peyton's right. 13 pi tenths? You got it in the right quadrant. This is like a Two's Clues problem. No. If anyone has the answer, yes! Freiberg got it. Is it Freeberg or Freiberg? Freeberg. Like Free Bird, like the song by Leonard Skinner with a G. Free iceberg, free bird. Okay. I would normally tell you to take your earbud out, but since you got the right answer, it must be working for you. I get it. You're not listening to last year's lecture in that year, are you? And then I gave it away. Anyone else get negative 3 pi tenths? No one else? Freeberg, you want to talk us through how you did it? Okay, let's stop right there. Let me catch up with you. We figure out where 13 pi tenths lives. We notice they're inverses of each other. So it could be that the answer is 13 pi tenths if 13 pi tenths is in the PVR. Freeberg, what quadrant does 13 pi tenths live? It lives in quadrant 3. Good. This is 10 pi tenths to pi. And then we go past it by how much? We go past it by 3 pi. So this reference angle is 3 pi tenths. Okay, good. Now what, Freeberg? Which is 3 pi tenths. Well, how'd you know it's in quadrant 4 and not quadrant 1? Well, you got the right answer, but here's the explanation that may clear it up. In this quadrant right here, where 13 pi tenths lives, is sine positive or negative there? Sine of 13 pi tenths is negative. It's less than 0. What's the other quadrant in the PVR where sine is negative? Quadrant 4. That's how we know we want to land in quadrant 4. Because sine is negative also in quadrant 4, and that's the PVR. So now that I know I'm in quadrant 4, I want to get to the same terminal ray in quadrant 4. I want to get to the same terminal ray in quadrant 4. The question is, do I go all the way around counterclockwise to get there? Or do I go straight down to it? I go straight down to it, which is the negative direction, and of course the reference angle is the same. Negative 3 pi tenths. Good job, Patrick. Does that make sense? Any questions, bless you, on that? All right, good. Let's try letter E. Sine of inverse sine of 4/3. So the first thing I'm noticing is that these are inverses of each other. Is 4/3 an angle or a ratio? It's a ratio. Is it a legal ratio? It's not a legal ratio. It's bigger than 1. So is there even such an angle? No. It's DNE. Yeah. So if you just put 4/3 there, that would be an answer choice on a test, on a multiple choice question. It would be wrong. It's not a legal ratio. So anytime the ratio is greater than 1. Or smaller than -1. Okay. It's DNE. Right. Good. Okay. So this one right here, letter D, is important that you know how to do that type of problem. Okay? It's a twos problem. We've already done that type of problem this year. It's just the instructions are packaged a little bit differently. You got to know about the PVR to do that one. All right. Do y'all want to meet inverse cosine today? No? I told him last night he was going to meet y'all today. I don't want to. He couldn't sleep last night. He was so excited to meet y'all. I was like, our flight got delayed though. Let's just meet inverse cosine and then we'll stop. How about that? Let's meet him. I don't want to disappoint inverse cosine. Let's graph a couple of cycles of cosine. Okay, so for cosine, it's kind of the same as sine. It goes up to 1, it goes down to -1. I'm going to come out to 2 pi, bisect it pi halves, bisect that, 3 pi halves, so on and so forth. -2 pi, -pi. Your pros at setting this up now. -pi halves, -3 pi halves. So they're setting the table. Now for cosine, we start differently. It's cha-la. So it starts at a high point, and then axis, then low, then axis, then high. Then going backwards, axis low, axis high. And then we connect them with nice, smooth quarter cycle arcs. Turn in the corner, show that it keeps going. Now cosine, of course, this is cosine, f of x equals cosine. Cosine is, of course, a function. It passes the vertical line test. Yes, yes? But is it a 1-to-1 function? No, because it fails the what? It fails the horizontal line test. So it is not a 1-to-1 function. So if we want to talk about the inverse cosine function, where there can be only one output per input, we need to make this a 1-to-1. In other words, we need to restrict the domain like we did for sine. Very good. There's three criteria. Let me remind you of the three criteria. We want it to be convenient, sorry. We want it to be convenient, so we want it to be near the origin, as close to x equals 0 as possible. We need it to be 1-to-1, so the part that we restrict has to pass the horizontal line test, but here's the kicker. It has to include all of the y values from negative 1-to-1. So for sine, we had to straddle the y-axis from negative pi f's to pi f's. But as Peyton already pointed out here, if I just look at the graph from 0 to pi, that's kind of nice, isn't it? It meets all three criteria. Oh, yeah, let's look at negative pi to 0. Would negative pi to 0 also work? Yeah, both of those are convenient. They're just as far from 0 as each other, right? They're just as far. They're both pi units away on either side. They're both 1-to-1, the green and the yellow piece by themselves, and they both contain all the values between negative 1 and 1. So let's take a quick vote in the classroom. Would y'all rather restrict it from negative pi to 0 or from 0 to positive pi? Raise your hand if you want the green portion in negative lane. You're not even going to raise your hand, Brady? That was your idea? No, it works. It works. Who wants the yellow piece? There we go. You see? And so when the meeting was voted on long ago when they were programming your calculators, they did the same vote. And I think one weirdo voted for the negative one. He's like, I'm a negative person. I'm going to go negative. I like being negative. It's going to rain today, I hope. Right? Maybe that'd be a farmer. I need the rain. Okay. Most people voted for the positive because positives a little bit easier to work with than negative. So that's where we restrict the domain. We restrict the domain on the interval from 0 to pi. Okay? From 0 to pi. Now, if you reflect that across the line y equals x, let's just draw what the new graph's going to look like. The new graph is going to be f of x equals either inverse cosine or arc cosine with two c's, arc cosine of x, either one. All right, let's go ahead and plot a couple of points. What happens to the point 0, 1? It becomes 1, 0. Okay? What happens to the point pi halves 0? It becomes 0 pi halves. That's the y-intercept. And what happens to the point pi negative 1? Negative 1 pi. So we get those 3 points kind of in a straight line, but it looks like this. We connect them like this. And then the rest of the graph, if you wanted to do it as a dotted line, it would snake back and forth left and right across the y-axis. So there is your graph of inverse cosine. He's entirely above the x-axis, all right? So what's the domain of this function? Negative 1-to-1. That's the same domain as arc sine, isn't it? These are your legal ratios. So just like arc sine, you cannot take the arc cosine of a number that's bigger than 1 or smaller than negative 1. They're not legal ratios, and that's because the cosine ratio, remember, is your other short leg to the hypotenuse. It's the horizontal short leg to the hypotenuse, so it has to be magnitude-wise less than 1. Now, what's the PVR, the principal value range of our cosine? 0 to pi. Yeah. And does it have any symmetry? Like arc sine still had symmetry. Does this one have any symmetry? What kind? Does it? You fold it on the y-axis and it lines up with itself? I don't see that. What about origin symmetry? Can we rotate it 180 degrees and it's the same graph? No. Poor guy. This guy has no symmetry. Unfortunately, there's no symmetry. But here's the unit circle implication on the unit circle. from 0 to pi, passing through pi halves, here is the PVR of arc cosine of x. It's positive in quadrant 1, it's negative in quadrant 2. So I like to think of the PVR for arc cosine not as the half moon, but as the sunrise. Yeah, as the sun on the horizon. If you want to think of it as sunrise or sunset. And the easy way to remember that is cosun, right? It sounds like cosine. Cosun. It's the sun on the horizon. So here's the consequence of this. You're never going to get a negative angle when you take the inverse cosine of something. Like you did for sine, right? If you took the inverse sine of a negative ratio, you're getting a negative acute angle. You're never going to get a negative angle for arc cosine. But you might get an obtuse angle, right? Positive ratio means positive acute angle. Just like for arc sine. If you take the arc cosine of a positive ratio, you're going to get a positive acute angle. But it's different for the negative. If you take the inverse cosine of a negative number, you're still going to get a positive number, but now it's an obtuse angle. It's between pi halves and pi. All right? So will arc cosine ever give you a negative angle? No. It's either positive acute or positive obtuse if it's a negative ratio to start with. Okay, so remember we got sine is the half moon, arc sine is the half moon, and then arc cosine is the cosun, cosun on the horizon. Cosunrise, cosunset, whatever you want to call it. Cosin, cosin, cosin. All right, let's try some of these. Example 8, we'll call it a day. We just need to reinforce this real quick. All right, so let's pretend that we're talking about the function, not the operation. What's the arc cosine or the inverse cosine of square root of 3 halves? First of all, what quadrant it's going to be in? It's a positive ratio. It's in quadrant 1. Let me give you a hint. All of the inverse trig functions that we're going to learn, if it's a positive ratio, they're all going to be quadrant 1. They all have quadrant 1 in common. Now, what's the other quadrant where cosine is also positive? Quadrant 4. But we're not interested in quadrant 4, are we? The PVR is quadrant 1. So what is the angle in quadrant 1 where the cosine is square root of 3 halves? In other words, cosine of what angle square root of 3 halves? It's using the unit circle inverse. Pi 6. There's your answer. Pi 6. Got it? All right. Arc cosine of negative 1/2. Which quadrant is it going to be in if it's the sun on the horizon? Quadrant 2. What's the angle in quadrant 2 where the cosine is 1/2? It's the pi thirds reference angle, but pi thirds is in quadrant 1. So what's the pi thirds angle in quadrant 2? 2 pi thirds. Yeah. Now, why is it not 4 pi thirds? What's cosine of 4 pi thirds? Yeah, cosine of 4 pi thirds is also negative 1/2, but it's in quadrant 3, which is not in the PVR. So we only look at quadrant 2. Got it? Okay. How about cosine of 0? Cosine of 0, man. Here's where cosine is 1. Here's where cosine is 0. Here's where cosine is negative 1. So where is cosine equal to 0? Pi halves. Yeah. Let's just do a couple more here. What's the inverse cosine of 1? 0. What's the inverse cosine of the arc cosine of negative 1? No. Pi. Very good. Pi. Yeah, so those are your quadrantal angles. This is 1, 0. This is 0, 1. This is negative 1, 0. So you got 1, 0, and negative 1. That's going to be at 0, pi halves, and pi. All right, what's our cosine of 5/7? Is 5/7 a unit circle angle? It is? I don't think so. What quadrant is it going to be in? It's quadrant 1. If we had the calculator, could we type that in? Yes, I'm not going to type it in. I'm just going to say it's in quadrant 1. How would you type that into your calculator? Yeah, second cosine, right? That's how we type it in. Second cosine in radian mode of 5 divided by 7. No, because I'm not asking you for the tangent of arc cosine of 5/7 or the sine of arc cosine of 5/7. I mean, we could draw a triangle. I could draw a triangle. I know this is 5 and this is 7, and this is going to be the square root of 7 squared minus 5 squared. But once I have all three sides, it doesn't help me find the angle theta, does it? The other problems where we did that, we actually had a double. It was a composition. Okay, so if I had like the sine of arc cosine of 5/7, then I can pull off the sine ratio. See what I mean? But I'm not asking you for the sine of that. I'm just asking you for the arc cosine of that. So we don't know what the angle is. It's quadrant 1. You can type it into your calculator. I'm not even gonna bring up the Minnesota calculator for that. Or should I? What is it? 0. What? Okay, thank you. All right, so that's it. Y'all met Art Cosine today. It was his pleasure. Let me tell you, it was his pleasure. He enjoyed it. Now he can get to sleep tonight because he has met y'all. We'll stop right there. Tomorrow we'll pick up with compositions of cosine like we did for today. So you have some time to work on your homework. Okay, so that wasn't a down day, Brady, but it was a shorter day, right? All right. Let's see. Should we be able to finish this tomorrow? Probably not. We'll probably take 2 more days to finish this. We're looking at a Wednesday. We're looking at a Thursday finish. So we're looking at a Friday worksheet due. We're looking at a Friday worksheet due. Should we quiz tomorrow? You don't want to quiz over arc sine? You know what? We should wait 1 more day so that I could quiz you over arc sine and arc cosine. More information. Let's quiz on Thursday. We'll quiz Thursday. And maybe Friday. And maybe Saturday. Let's quiz Sunday at 8 p.m.